Today we're going to look at classifying different types of polynomials. One of the ways we do that is talk about if they're even polynomials or odd polynomials, different types of functions. Okay? And we call those symmetry, how they look, and think about a mirror. Okay? Even symmetry polynomials have a vertical mirror down them. Okay? A parabola looks the same on the left as it does on the right. But to be considered even symmetry, they specifically have to be symmetrical across the y-axis. So this first picture over here, okay, if I think of this as my y-axis right down the middle here, everything that's on the left and the right of that has to look exactly the same. Okay, and we can prove things have this symmetry if, using function notation, f at negative x equals f at x. Now that might sound a little bit confusing, so let's look at some points here. If I took f at negative 1, that would be this point right here, right? Its value is 1. If I look at its symmetrical point, so f at positive 1, it's also 1. So I've shown that f at negative 1 equals f at positive 1. They're the same. And that should be true for every single point on this for it to be even symmetry. Try another one. F at negative 2 comes out to 4. F at positive 2, 1, 2, 3, 4, also comes out to 4. Hey, they're the same value. This is even symmetry. If you look at the one on the right-hand side here, well, obviously, from a visual perspective, the things on the left-hand side of the parabola, left-hand side of the axis, and right-hand side of the axis definitely do not look the same. Right? This one's over here, this one's just a little bit. Mathematically, if I tried, let's say, f at 1, what's that come out to? F at 1 is right here, it's negative 2. F at negative 1 comes out to, negative 1's right about there. I'm going to say it's about negative 0.5. Those are not the same values. And because they're not the same values, this cannot be even symmetry. Okay, so we can look at pictures and figure this out. We can look at points and figure this out. We can look at equations and figure this out. So I want to know if these things are symmetrically even using some algebra. So I need to prove that f at x is the same thing as f at negative x. Well, I see it f at x. Here's f at x right here. I need to calculate f at negative x. Based on function notation, I can do that by replacing every x that I see with a negative x. So if I take my original equation, 3x, we'll replace the x's with negative x's, and then simplify, okay, I can check if this thing is even. So remember, we said to be even, f at x should equal f at negative x. So let's check. Does that look the same as that? Well, they don't. They're not equal. So we'd say they're not even. Okay, we can try with the second one. I want to check to see if this is symmetrically even. So every time I see an x, I'm going to replace it with a negative x. I see an x. In fact, I see an x squared. I'm putting in brackets, remember, I want to apply my exponent to the whole thing. Plus 5. Let's simplify this. What's negative x squared? A negative x times a negative x makes a positive x squared. Are these the same things? Well, for sure they are. F at x equals f at negative x. Therefore, this is even. Proved it. Without having a picture, we're going through a whole bunch of points. Okay, let's try another one. Let's see what happens at negative x. Every time I see an x, I'm replacing with a negative x. Every time I see an x, I'm replacing with a negative x. Exponents first, BEDMAS, right? Negative x to the power of 4 means negative x times negative x times negative x times negative x. 4 x's. 4 negative x's specifically. 4 negatives makes a positive, so I get x4, minus negative x squared. Negative x times negative x. Well, 2 negatives make a positive, so x squared. Let's check it out. Does that equal that? Sure do. So fx equals negative fx. This is even. Okay. Now this is how I can prove it, but there's something I should know. Okay. Algebraically, a function is only symmetrically even if all of its exponents are even. So look at the last one we just did. I got a power of 4 and a power of 2. Well, those are both even numbers. I knew it was going to be even before I started. Going back a second, I had a power of 2. The 5 doesn't have a power, but if you stop and think about x to the 0, you can think of that as an even number, I suppose. Okay, so 2 and 0 are even. That's going to be an even thing. If I look at the first one, it has a power of 1. That is not an even number. There's no way it should have been even, and we, in fact, proved it wasn't. And there's our first type of symmetry. The second type we call symmetrically odd. Now this symmetry is a little bit more tricky to look at. It's rotational symmetry about the origin. So by that I mean the top right quadrant looks the same as the bottom left quadrant. So if you can think of this as it's been flipped horizontally and then again vertically. So a double rotation or a double reflection, if you will. Okay. So obviously this first one is symmetrical with the origin. If I look at the second one, okay, this piece here has been flipped to that piece there. This piece here has been flipped to that piece there. And that looks symmetrical with the origin. It's a little bit harder to figure that one out. So let's look at this property idea. Okay, in this case, f at negative x has to equal the negative of fx. So we'll go back to the first one for a second. That's the easiest one to think about. Let's pick some nice points here. So f at 1, what does that equal? F at 1 is right here. It's 1. Okay. Based on my idea here with this formula, I got to figure out the f at negative x. So f at negative 1, what does that equal? That's right there. It's negative 1. Now this time, those are obviously not the same, but we're not trying to show those are the same. Okay, we're trying to show the negative of fx. So the negative of f at 1. So I need the negative of the answer. The negative of the answer, it used to be 1, now it becomes negative 1, right? The negative of my original answer. And if things are odd, these two things are the same, which in this case they are. Okay, f at negative 1 equals the negative at f at 1. Yeah, it's odd. We can try the second one here, same ideas. Okay, let's find some nice points here. Let's try f at 2. It'll be right here. It's negative 2. Let's see what happens at negative x. Okay, that's up here. It's 2. And if I took the negative of my initial one, I'd end up with the negative of this. That's a positive 2. These two things are the same. That's odd. Okay, the third one is not. We can prove that. If I find f at 1, I get 3 this time. If I find negative 1, I get negative 1 is right here. And if I took the negative of the original thing, I'd end up with negative 3. Are these two things the same? Definitely not. Not odd. Okay, so we're going to go to pictures, we're going to go points. We'll look at some equations, how we can prove that. So my objective this time is to prove that the negative of the function equals f at negative x. So let's try the negative of the function first. The negative of fx equals the negative of the function, which means I can simplify that. F at negative x, wherever I see an x, I'm going to replace it with a negative sign, simplify, and then check out these last two versions. Hey, they're the same. Okay, so negative fx equals f at negative x. Therefore, it's odd. We've proven it. Okay, let's try the second one. I'm going to take the negative of the function, so the negative of the whole thing, negative x squared and plus 2. Let's try f at negative x. Every time I see an x, I'm replacing with a negative. If I square a negative, it becomes a positive. Are these the same? Most definitely not. Okay, so since they're not the same, we say they're not equal. This is not odd. And before you started that one, I'm hoping you recognize that this should have been an even function, right? Even exponents. Even exponents. Okay, so we can pretty much prove it's not odd just thinking about it, but algebraically we have to do the math. Okay, last one. Let's take the negative of the function. So the negative of the whole thing. Expand my brackets. I got a plus x this time. Okay. Or if I take the negative x version, so 4 times negative x to the 3 minus negative x. Negative x to the 3, that's 3 negatives. That's going to be a negative answer. So this comes out to negative 4x cubed. And when I subtract a negative, two negatives beside each other makes a positive. Let's check them out. Are these the same? Sure are. So since these two things are equal, this is an odd function. And I'm hoping you thought ahead already a little bit and kind of maybe recognize that. Just like you can prove even things are symmetrical if they have even exponents, well, odd things are symmetrical if all the exponents are odd. And if you look back at the last one we just did, sure enough, our exponents are odd numbers, right? Which tells me, oh, it should be odd. And the one before that, that was even exponents. We know it's not odd. The first one, 2x to the 1, odd exponent, odd answer. It should kind of make sense that way. Okay, try the last one. You proved which ones are even, odd, or neither. There's a possibility it doesn't be something weird, okay, based on what you know. Try them yourself, see if you can work ahead, figure them out. Okay, to go through the two options. Okay, I'm usually going to start with the even option. Okay, I'm already thinking, looking at this exponent, oh, I got an even exponent and another even exponent. It should be even, right? So I'm thinking already, but I want to prove it. Okay, so I'm going to replace the x with my negative x. Okay, there is no actual x's there, right? Negative x squared. Okay, that becomes a positive. Hey, look, my things are the same. I knew it was even. I've proven even. And if I have to give a reason, I'm going to say because fx equals f negative x. Okay, look at the next one. I see an even exponent and an odd exponent. I should know in my head this is going to be a neither situation, but I need to prove it. So let's prove it's not even, first of all. Negative x, negative x. 3 negatives make a negative. 2 negatives make a positive. These two are not equal, it's not even. Let's try the other option. The negative of the whole function. The negative of the whole function. That gives me negative x cubed minus x squared. I check out these two things. Are they the same? Note the sign in the middle is different. So there's no comparison in any of those things. This is no symmetry whatsoever, not even or odd. Okay, last one. Look at, I see odd exponents. I can tell that right off the bat. I've got a power of 3. I've got a power of 1. I should know this is odd. Let's prove it. Odd means the negative of the function. So take the whole thing and simplify it. Should equal f at the negative x. And if we try that, negative cubed plus a negative, 3 negatives, my exponent of 3 makes a negative answer. And if I add a negative, it's like subtracting. I should have a cubed on it. And if I look at these two things, sure enough, hey, they're the same. This is an odd function. And I know that because f negative fx equals f and negative x. Okay, try the homework. That's just a sheet tonight. Check your answers on that, and then move on to the next one function. Next lessons. The next couple deal with technology, so you're going to have access to a computer, an iPad, a phone, something like that, so you can access the technology online.